So just so make sure everyone has seen this, the structure for final exam. Pretty, I mean, clearly laid out. You're going to have one problem where you have a function of two variables. Got to find the domain, find the intercepts, sketch the traces, which we can definitely talk about today because I feel like that's something we didn't cover very specifically. Show the limit does not exist, right? She's not even exist or not exist. She's telling you it's not going to exist. You just have to show it. So how do we do that? How do we show a limit doesn't exist typically for a function of two variables? Right, because I say two paths, not two points. Yeah. Maybe. Sure.
That would be like y is x.
Right, y is x, y, or, and I would remind everyone, we'll do an example here in a minute, that y equals 0 and x equals 0 are excellent paths to use because they almost always give you 0 back. Not always, but often. Partial derivatives, chain rule. Yeah, we can go through that. Directional derivative, yeah. Linearization. Compute a double integral. I would certainly say double integral. For me asking the question, I would definitely ask one where you had to change the order of integration, because that is just a more interesting question, in my opinion. I believe so, yeah. Finding and classifying critical points. That's where we take the partial, set them equal to 0, find the critical points, and then use the second derivative, the d thing, right? The fxx fyy minus fxy squared to see if it's concave up or concave down or a saddle point. What else? And then the rest of this stuff, well, the next two things are right, the solving. I feel like I don't love that phrasing. Solve the initial value problem. The way I would, that's solve the differential equation and then use the initial value to find the C1 and C2. Classifying equilibria. So I will say, for everybody, classifying equilibria should be relatively straightforward because she's giving you all of the classifications on the front page. Right? I mean, there's literally, I forget, let's take a look real quick here. Because I saw it just a moment ago. If you look here, if you look back up at, sorry, it's all over the place here. So this is, so fall 2023 17C final exam front page. She is telling you this is going to be on the front page. And it's literally the same thing I just showed you. It's all of that. So look at what you're being given on the front page here, just so you know what you don't have to take time to memorize. We are given, okay, organize your work, show your work, and then she's giving you the chain rule. So that df dt is df del f del x times dx dt plus del f del y times dy dt. And you could add on more, right? If it was a function of 3 variables, you'd also have like a del f del z times dz dt, et cetera, et cetera. For critical points for functions of 2 variables, she's telling you what the d thing is you have to calculate. She's even giving, wow, this feels quite generous to me, in my opinion, right? She's telling you if your d is positive and your second derivative is positive, you have a minimum. If your d is positive, your second derivative is negative, you have a local maximum. And if your d is negative, you have a saddle. How kind. And then she's giving you all the conditions. I don't love the way, it's okay, fine. She's giving you the conditions, not the way I would have written them personally, but she's giving you a way of determining if you have all the things in your graphic, right? Spirals, nodes, stable, unstable, saddles. Now, if it were me personally, if I was taking this test, I would go and say, yes, that's true, but I would also say lambda 1 positive, lambda 2 negative, because that's how I think about having a saddle. Is one of the eigenvalues is positive, one of the eigenvalues is negative. And then for being unstable, that's where both lambda 1 and lambda 2 are positive. For stable, lambda 1, lambda 2 are negative. And then these last 3 are spiral things, which means our eigenvalues are, yes, complex. So here we have lambda equal to a plus or minus bi. And if it's a center, b is equal to 0. If it's a, we did not, oh god, oh no, I apologize. Wow, this is, okay, this is fine, but it's not the way I would have written it. She's giving you more general conditions, which is not bad. Sorry, I think, yeah. So here's how I would do it personally. You can use this, it's great. I shouldn't have said all this though, really, over here. I would have just said, I like the 6 classifications personally. I'm gonna say saddle, lambda 1's positive, lambda 2 is negative. And then we have a node, a stable node, if they're both negative. We have an unstable node if they're both positive. And then we have spirals. So we have a center if lambda is just purely imaginary. It's plus or minus the BI part. And then we have an unstable spiral when it's A plus or minus BI and A is positive. And we have a stable spiral if A is negative. That's the way I prefer to think of it. You should do whatever you like though. Correct. Yes. Yeah. So this is, I'll say, I like this personally, especially if it's a nice regular system of 2 linear differential equations. But when you're doing the whole Jacobian thing, sometimes it is easier to look at this condition versus this condition. But either way is fine. And I would say pick one way to do it and make sure you're comfortable doing it that way. And then she's got this whole terrible formula down here for the complex eigenvalue eigenvector thing, which was that on the second exam? It wasn't. Well, no, it's just that was there a problem where you had to use this formula on the second exam? Okay, great, cool. So honestly,
Make it.
right, like if it were me and I actually wanted to ask my students a question like that and I didn't put it on the second exam, I might put it on the final. I might not, because and here's why I might not. I might not because I don't want to give myself the grading headache that I know it's going to be because so many people are going to fuck it up. But like, it's right, exactly. I don't think there's a lot of value in that question, but I'm not the one writing the test. So take for that what you will. And then of course, there is all the probability stuff that we've been talking about since the last exam. So that is what we've got there. And yes, so there's going to be some probabilities. Ooh, independence. So when you think about independence, you should think that the probability of A given B is equal to the probability of A. That's the way I like to think about it, because you're saying knowing that B happened doesn't change the probability that A happens. Now, another way of thinking about this is that the probability of A intersect B is equal to the probability of A times the probability of B. This is only true if they're independent. This is not generally true. If A and B are independent. Or in other words, if you're trying to show they're independent, you try to show that one of these two things is true. And they're really the same thing. There's just a different version of the same formula. And then 2 base formula questions or other, that's very specific. 2 base formula or other.
There's going to be choose 3 doors, not.
Choose 3 doors. I don't think we talked about that.
No, it's gonna be. I forget the name of it. It's like what game shows do.
Oh, sure. It's called the Monty Hall problem.
Yeah, that.
Right.
There will be.
Exactly. Yes, that is, yeah. Let's see what's in the chat here. How do we show independence? Ooh, I wouldn't know how to show the independence of 3 or more events. Usually you try to show 2 events are independent from each other. I don't, I don't know. It's on the exam. Okay, which one? Take a look. I'm curious. Let's see here. So I've got all the exams here. What's that? No, we're definitely not doing ANOVAs, not a stats class. I know. Let's take a look here. If you know which one, maybe tell me, but otherwise I will hear. Oh wow, that's a lot. Okay. I think it's on that one. Oh wait, maybe there. Oh, no. That last question's funky though. Look at that one. Sorry, one sec. Let me try and find this question. Part number 9, part M on final 1-3. Okay. Part M? There's a part M. There shouldn't be a part M of anything. Terrible. Okay. Okay, so let's take a look at this problem. So we have in a survey, 65% of respondents said they consume alcohol, 20% said they consume marijuana, and 5% said they consume both. What is the probability that a randomly chosen person from this population will be a consumer of at least one of these substances? So I don't think that question is asking us to show that those are independent of each other. So this question, if I'm reading the right question, is telling us, so let's say that alcohol is A, or consumes alcohol, and M is consuming marijuana. And so here's what they've told us so far. And I definitely, when you read these, you want to kind of write down the pertinent information. So the probability that someone consumes marijuana is 65%. And that's what we mean when we say 65% of people do that. It means if you just randomly grab someone from the population you're surveying, there's a 65% chance that you grab someone who is consuming alcohol. 20% consume marijuana. And then 5% consume both. So the probability of A intersect M is equal to 0.05. So that's what we've been given. Then they're asking us, what is the probability that a random chosen person from this population will be a consumer of at least one of these substances? Which is the nicer way of wording it. Because they could have also asked the same question by saying, what's the probability that a randomly chosen person consumes marijuana or alcohol? And when you say or in math, you mean one or the other or both. That is what they're asking us for. And so it is literally these words. What is the probability that a randomly chosen person from this population will be a consumer of at least one of these substances? That is the part that is telling me. Oh, it's this one, it's alcohol or marijuana or both, right? Because at least one of is one or the other of both. It's practice final. Oh, sorry. Well, let me finish this question since I started it, and then we'll look at that one. So final one. Okay. We'll take a look there in a moment. Practice final one. I mean, that's okay. Anyway, so to answer this question, the probability of A union M, it's the probability of A plus the probability of M, and then you have to subtract the probability of the intersection because you've double counted their overlap. You counted the overlap when you counted all of A, and you counted the overlap again when you counted all of M. And so we have to subtract off the overlap. This is called the inclusion-exclusion principle. And that's going to be whatever it is, right? 0.65 plus 0.20 plus minus 0.05 is going to be 0.8. Okay. Let's look at the one, sorry, let's look at the actual one. Let me make sure I've got the right thing here. 2 plus 1. Okay. 9 M. I still don't see this being a question. Maybe so. Is it this question? Is it the one about HIV and tuberculosis? Okay. Is it the one? Did I miss one of the practice finals? Is it the one about having a particular type of cancer? Or is it? Did I miss a page here? Let me take a look. Let me, sorry. It's about cars. Okay. Let's see here. I thought I printed all of them out. I guess maybe I didn't. Let me hide this for a second. Sure. So let's just go back to her modules. Sorry, one second. That's not where I want to be though. It's just way down the bottom. Okay, so it's practice final 1. I think I might have lost the page when I printed it out. Gosh, so many pages. I mean, I definitely write tests where I give students a lot of pages because I like them to have lots of room to write out their work. Okay, so we've got cards here. I really thought I had this one. I guess not, though. It's not that one. It's not that. Yeah, it's not any of the ones I have here. It's definitely not that one. I think I missed the pages on that one. The problem. Oh well. Okay, so let's take a look. So, question M. Okay, are the events A, B's? Okay, so let's go ahead and see what B and D are. So let's put some blank paper here. The independence is so gosh. It seems like it'd be weird to ask a question where about a thing. I guess technically you've talked about it, but it seems a little bit challenging here. So let's see. So event B is that the rank of the card is a jack or higher. So B is that the rank is jack or higher. And since we're writing this down, let's go ahead and write down the probability. Oh, sorry, you can't see what I'm writing. Apologies. So, how many ranks are there that are jack or higher? There's jack, there's queen, there's king, and yes, ace counts as high and low, so we're going to count it high because we can. Yeah, ace counts as high and low. Right. Some card games don't do that. We're considering the card game we're talking about is poker. Almost every stats or probability example when you're talking about cards, if you're talking about games, is usually talking about poker. Not always, but most of the time. Aces, well, ace, I don't want to say that. Ace can be high or low. Because you can have, so let me point out, and this would be a terrible question to ask on a test. How many ways can you get a straight? Well, you can get a straight ace, 2, 3, 4, 5, all the way up to 10, jack, queen, king, ace. Ace counts high and counts low. Those are the rules. I didn't make them up, but they are the rules. Do you have a question, Maddie? Not for this question. Rank is jack or higher, jack, queen, king, king, ace. Everyone in the world is going to say yes, ace counts high. I'm not saying that's a good question or a good thing, but I'm telling you the reality. The reality is, unfortunately, we use card examples a lot and we just assume inappropriately that everyone knows how a deck of cards works, which is definitely not the case. There are plenty of people I've talked to in this class. They're like, I've never played with cards in my whole entire life. So it's a little bit unfair. And unfortunately, that's how some of these classes end up being. But that's neither here nor there. We just have to deal with the reality right now because you have a final next week. So jack or higher, meaning jack, queen, king, or ace. What's the probability of picking a card that is one of these ranks? I don't want you to say 16 out of 52, even though that's correct. I want you to say 4 out of 13. 4 ranks you could pick out of 13 total ranks you could pick. It's the same as 16 out of 52, but I'm reducing what I have to think about. There are 4 ranks I could pick that are meeting the requirement out of 13 total ranks I could pick. Okay. What's the second part here? Sorry, it's terrible. Yeah, I was like cars. Yeah, cards. Okay, so sorry, I'm gonna have to go back and forth here for a minute. All right, so event B, oh, we don't care about A. C is the event that the card is spades. So C is spades. What's the probability of pulling the spade? 1/4, right? 1/4 of the deck is spades. I know you can't see that, but I wrote down I wrote C equals spades and P of C equals 1/4, and then we'll go that. And then finally, D is the event that the card is an ace. And the probability of drawing an ace is what? Say that one more time. Not 4 over 13. You could say 4 over 52 or 1 over 13. Right? Because again, if we're talking about, so the rank of ace, there is one rank that includes all aces. It's all the aces. And out of 13 ranks. Or it's 4 aces in the deck out of 52 cards total. Same number. Right? This is equal to 4 out of 52. Just like this is equal to 13 spades out of 52 cards. Just like this is equal to 16 cards out of 52 cards. But we want to use the easier numbers to think about. At least I think we do. And then I did that too soon because I still have to go read the question. Okay, so now the question is, and I think we might want to do one of the previous parts before we do that. Oh, just as a quick aside here, let's go ahead. We might as well just work through most of this question, just to kind of get there. The event A is that the card is red. So if A is being red, sorry, it made me think of a quote from a movie. Yeah, I imagine, haven't you seen Rounders? Well, you're missing out. It's a good movie with Matt Damon and what's the other guy's name? Edward Norton. Anyway, at one point they're teaching some very rich people how to play poker, and one guy's like shows off the cards. He says all red, but it's not a flush because they're like diamonds and hearts, and it sits in my mind as like all red. Anyway, what's the probability of having all red? Or sorry, not all red, of drawing a red card. Sorry, 1/2, right? Half the cards are red, half the cards are black. Okay, so now, again, sorry for the situation where I have to keep looking at this here, but that's what I'm stuck with. What I wanted to point out is specifically number E here. So E is asking what's the probability of A minus B? That's what that notation means. It's all the things in A less all the things in B. So how many cards are there that are red? Right, half of 52, which is 26. I always remember that the number of cards in the deck is twice the number of letters in the alphabet. I know it's kind of silly, but it works for me. There's 26 letters in the alphabet, and there's 52 cards in the deck, and 26 is half 52. And then B is rank of Jack or higher. Okay, so A consists of all red cards, meaning ace of hearts, ace of diamonds, 2 of hearts, 2 of diamonds, all the way up to queen of hearts, queen of diamonds, king of hearts, king of diamonds, ace of hearts, ace of diamonds. How many of those cards are also in B? And I didn't list them all. Well, the aces, the kings, the queens, and the jacks I didn't write. So 2, 4, 6, 8 of these cards are in the set B, because B is the set of all cards whose rank is Jack or higher. So A, right, B is all 4 jacks, all 4 queens, all 4 kings, all 4 aces. And A minus B is the set of all the red cards up to 10s. So red aces, red 2s, all the way up to red 10s. But not the red jacks, the red queens, the red kings, or the red aces. Oh, sorry, I said red aces. See, I'm making the mistake that I was worried I was going to make. Red aces should not be included. There you got, right, because the red aces were in set B, so we need to exclude them so they are not in A minus B. Again, right, that's what that means. This is A minus B. So everything that's in A, take away everything that was in B. How many cards are we left with? Let's see. 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 9 ranks and 2 red cards in each rank. So there's 18 cards total. So the probability of A minus B is 18 cards we want out of 52 total possible cards. And I wouldn't worry about reducing fractions here unless you specifically are asked to. Yeah, it's a backslash. Right. The vertical line is a conditional probability. The backslash is set subtraction. Set subtraction. If you want, it is, I don't like this notation, but it is not incorrect to write literally A minus B. As long as you know that that's what you're doing, it's fine to write that. You might, I should say, it is genuinely accepted as being fine. You might want to ask her if it's okay for you to write that. It should be fine. It is accepted notation. It's not preferred notation for me personally, but questions about this?
Also,
That is A intersect B complement. Yeah. So A minus B is the same as everything that's in A and everything that's not in B. So the overlap of all the things in A and all the things not in B. Oh, so I don't know how many of you are on the Discord for this class, but someone shared a really great graphic on the Discord of all the set intersections. I would encourage you all, if you're not on the Discord, to jump on it and look at that graphic, because it's a nice picture. In fact, I'll probably, if I remember to do it, yeah, exactly, the Venn diagram graphic. I'll try and see if I can post a picture of it on campus for everybody, because I thought it was really nice. Say that one more time. Right, ace of hearts, ace of diamonds, two of hearts, two of diamonds. Yeah, sorry, yeah, that's the two, believe it or not. Okay, so moving along here to the actual question that was asked. We're almost there. I think we need to do one or two more things first. Sure. So the question here is, yeah, are the events B, C, and D pairwise independent? So pairwise independence is not hard to figure out. Let's answer that one first before we try to tackle the other one. But I think she's even telling you what you need to show for the other one. So pairwise independent. So for pairwise independence, B, C, D, pairwise independent. When you say something is pairwise true, you just have to show that it's true for every pair. So we have to show, we would need to show that both B and C independent, B and D independent, and C and D independent. That's how we would show that these three things were pairwise independent. So let's remind ourselves what we've got here. So I'll just remind you, B is ranked jack or higher, C is spades, D is an ace. So I feel like they're not going to be pairwise independent because there's some overlap, but let's see. So let's do, sure. And so what I should say here really is having done the previous parts is what's going to allow you to do this part easier, right? Like if I'm looking at this question here, I'm really going to be using the fact that I've already done these calculations up here. If I already know what the probability of B given C is, okay, well, let's find the probability of B given C. So the probability given C, I'm always going to calculate this conditional probability as B intersect C divided by the probability of C. Okay. B intersect C is, well, B is ranked jack or higher. C is a spade. So we're looking for all the jacks or higher that are spades. So B intersect C is jack of spades, queen of spades, king of spades, ace of spades. There are 4 cards in there. And then C was the probability of being a spade. There are 13 cards in there. Notice how I'm writing this differently than I'm saying it. If I was really writing this as probabilities, I would write this as 4 out of 52 over 13 out of 52. Okay, what's the probability of B? Well, B was being, what was B? Well, we have it already on the previous page, right? What's the probability of B? 4 out of 13. Oh, those are the same. So B and C are independent. All right, let's do the same thing for B and D. Now I'm going to go back and look at the question to see if we had already supposedly calculated one of these probabilities. And I don't see one with B and D. That's annoying. Let's do C and D then. So let's find the probability of C given D, which is the probability of C intersect D divided by the probability of D. So it certainly looks like if you have a question formatted like this, which I wouldn't be surprised if you did, you should definitely try to do the problems in order, right? Because the later stuff, you're going to want to be looking back to the previous questions to not repeat the same work you've already done. So if I want to find this, well, again, C was being a spade, D was being an ace. So what's the overlap of C and D? Being a spade and an ace. How many cards are there that meet that criteria? One spade that's an ace. One ace that's a spade. And D was being an ace, and there are 4 aces. Or again, you could do it the long way, right? It's 1 out of 52 divided by 4 out of 52. And then we had already calculated that the probability of C was 1/4. So these are also independent. All right, what about B and D? B and D I feel like are not going to be, but I don't actually know. So B and D, let's find the probability of, sure, let's do it that way. Let's find the probability of B, let's find the probability of D given B. So let's think about this for a second. B is that the rank is Jack or higher. Actually, I want to do it the other way. Oh, well, that's fine. And D is being an ace. The probability of D given B, well, it's going to be the probability of D and B divided by the probability of B. So D and B, D intersect B is D is being an ace, B is being ranked Jack or higher. The intersection, the overlap of those two things is just being an ace. If you take the intersection of all the jacks, all the queens, all the kings, and all the aces, intersected with all the aces, you end up with all the aces. That's where they overlap. So one way to think about this from a Venn diagram perspective is that D is completely contained in B. Right? D is all the aces. B is all the face cards and aces. So the probability of D, given that you're in B, is going to be, well, there's a 1/4 chance. Oh, so, James. There are 4 aces out of 52 total cards. And the probability of B, that you're one of these 4 ranks, was 4 out of 13. Or if you prefer, I kind of do, 16 out of 52. Which leaves me with 4 out of 16, which is 1 out of 4. And the probability of D was not that. I feel like I might. I'm pretty sure I've done this right. It always feels a little bit confusing here. You all look like I might have made a mistake, which is possible. Let's double check our thinking here. So in fact, let me go so D intersect B, right? D is being an ace. B is ranked Jack or higher. So let's go the other way and say, well, there's 4 cards that meet that criteria, the aces. B was being ranked Jack or higher. Well, there are 16 cards that meet that criteria. Nope, it's still the same thing. On the other hand, the probability of D, which was being an ace, is 4 out of 52, which is 1 out of 13. So these are not. Let's check the solutions. It's always good to check your work if you can. Maybe I'm doing something stupid that I'm not aware of. Sure. I'm sure I've got this just already open somewhere. Sorry for there we go. There's the solutions. Right. Let's take a look here and see. I wonder what happened to those other pages. Yeah, so she is showing the same work here. And so she's doing it the other way, which is totally fine. I don't like doing it that way, but it might make more sense to do it that way. So another way to show that D and B are not independent of each other is to show that the probability of B intersect D does not equal the probability of B times the probability of D. We know what these both are. The probability of B was 4/13. The probability of D was 1/13. And the probability of B intersect D was 4/52 or 1/13. And those are not equal to each other. So one thing I'll point out is I did too much work for this problem. Because the problem asked whether or not these were pairwise independent. And I made it's not because I didn't do it on purpose. Like I made bad choices accidentally. I should have tried to look for the one that I thought might be not independent first. Because if I could have shown one pair was not independent, then the answer to the question is no. They are not pairwise independent because one of the three pairs didn't work out. So if any of the pairs are a no, then you're done. If all of them were a yes, then the answer is yes. So I should have tried to think about the one that I was pretty sure was going to be not independent. So there's two different ways of doing it. To show the two things are independent, you can either show, and again, these are really the same formula, but let me say it again. So to show that A and B are independent, I prefer to do it by showing that the probability of A given B is equal to the probability of A. But let me show you how you get from this formula to the other formula. The probability of A given B, the formula for that conditional probability is the probability of A intersect B divided by the probability of B equal to the probability of A. And if you multiply both sides by the denominator, you end up getting the probability of A intersect B equals the probability of A times the probability of B. So you can either show this or show this. I will tell you honestly, my brain always goes with this because it's just the way that makes more sense to me. But honestly, this is probably the easier calculation. So you should probably do it this way. I didn't mean to do it not that way. I just defaulted to this because that's always where my head goes when I think about independence. But either way is correct. But if you already know what A, the probability of A and the probability of B and the intersection is going to be, then checking that is relatively easy. Whereas over here, I was doing maybe more work than I needed to. Let's see what's in the chat here. I know we haven't gotten to the question yet. We're almost there. Don't you have to show the word for it? No, you don't. So the thing is, if you're trying to show or prove whether or not A, B, and C are pairwise independent, which I know this is the first time we were talking about this concept in this class, you either have to show that they all are, or at least one of them isn't, right? But if one of them isn't, then the whole thing is not pairwise independent. So if, for example, the probability of A intersect B does not equal the probability of A times the probability of B, then we can conclude the following. Then 1, A and B are not independent. And more generally, 2, the set of A, B, and whatever else you want to include, you can include everything, A, B, C, D, E, F, G, H, I, J, K, however many things you want. A, B, and C cannot be pairwise independent because not every pair is independent. And we do not have to check anything else. And I would really emphasize that fact here, because if you get asked a question like this, it'd be a pretty good bet that it's going to not be pairwise independent, and you should try to look for the one that you think might not be independent to try that one first. And my thought process here, when the reason I saved the one I did for last is I wanted to show you how all the other ones were independent. But I will point out, I was pretty sure that B and D were not going to be independent because B was being a jack, queen, king, or ace, and D was being an ace. And it feels like there's some overlap there. Like if I know that I'm an ace, then I'm pretty sure I know whether or not I'm a jack, queen, king, or ace. So yeah. So I would look for the ones that you think are independent to try to, that are not independent to try to disprove pairwise independence. No, so again, listen to the words I'm saying. I'm saying if one pair is not independent, then you're done because you cannot have pairwise independence. You're right. If one pair is, then you have to check the next pair. You have to keep checking pairs until they're either all pairwise independent or one of the pairs is not. Cool. So now let's check for the other thing, which is, what was it called again? I don't remember what it was called. It was called something terrible. Oh, it's over here. Sorry. Is it over here? Yes. Are they independent as a triplet? But notice she is telling you how to calculate it. So really, you don't have to do so much thinking for this part as just executing the calculation. So we're asking, is it true? And I can't even read the third part, but I'm pretty sure the thing we're asking is the probability of B intersect C intersect D equal to, I'm pretty sure that's going to say the probability of B times the probability of C times the probability of D. Let's check. Let's make sure though, before we just go on blindly here. Can we make sure? Maybe. Maybe not. I guess I've got it. Let's say I've got it over here. It does say that? Cool. All right. So, again, this is where you have to go back and remind yourself of what everything is. So, B is a ranked jack or higher. C is a spade. D is an ace. And the intersection of all those things is just all the cards that meet all three of those criteria. So we're looking for a card that is ranked jack or higher, also rank ace. So it's got to be an ace, and also a spade. And how many cards are there that do that? One. So this is just the one ace of spades. So the probability is 1 out of 52. And then we've already calculated these other three things. The probability of B was 4 out of 13. The probability of C was 1 out of 4. And the probability of D was 1 out of 13. And if you calculate that, it is not equal to 1 over 52. The 4's cancel, and you get 1 over 13 times 13. So no, they're not equal to each other. So since these are not equal, we do not have triple independence, or whatever you want to call it. Cool. Would what be a red ace of spades? So the overlap here, right? So B was a jack, a queen, a king, or an ace. C was being a spade, and D was being an ace. There's no red card here because we're not including event A. A was the event of being a red card. If we did, there'd be a 0% probability of getting that right because you can't have a red spade. Spades are black. In fact, I would point out that the probability of A intersect C is 0 because A is being red and C is being a spade, and there is no overlap. So you could say that events A and C are, what's the word we use? When things are disjoint or mutually exclusive. Yeah, that's right. Right. Disjoint, yes, mutually exclusive. Yeah, that's fine. Right, there is no card that is both a red card and a spade card. All right. What else should we look at? Oh, I said we should, I thought we should talk about trace for a minute, if you all think we should, I guess. I'm happy to talk about whatever you all want. I just thought trace seemed like a likely candidate here. So. Let's see. Let's actually, before I do the trace problem, yeah, let's fast. Look at that. We did one just like that. Let's do one more like this. Let's say our function was f of x, y equal to x squared plus y squared minus 16. Which is a little bit boring, but whatever. Not the point. So we want to find all the traces. Okay, and here's the thing I want to remind you all to remember. If you're finding the variable trace, then you're letting the missing variable equal 0. So if I want to find the xy trace, what am I going to let equal 0? Z. I don't see a Z there. What do we know is Z that we're not saying is Z? Right. When I write in 2 dimensions, f of x equals x cubed, what do we also call f of x? Y. Same deal here. We're thinking of this as our Z, our output. So in the xy trace, we're going to set Z equal to 0. And heck, I would give you points for writing that down. Yeah, they know what they're supposed to do. They're supposed to set Z equal to 0 and then figure out what the function looks like. So we set Z equal to 0, we're going to get x squared plus y squared minus 16 equal to 0. And here, you're not going to solve for y. I will say in the problem she has on practice final 1-3, because that's what I'm looking at, there you would solve for y. But we'll look at one like that too, just to kind of change it up. So here, oh, I know, I bet I know it. That's good. I would write this as x squared plus y squared equal to 16, and then know that I'm graphing a circle of radius 4. Okay. How about the xz trace? So then what do I set equal to 0? Right, the thing that's missing. Y equals 0. So then I'm left with z equal to x squared minus 16. And when you graph these, you should label your axes like I failed to do so here. For the xy trace, you want to label them the normal way, where x is the horizontal and y is the vertical. For the xz trace, we typically always label z as the vertical axis. So I'm going to label it like this. And then I've got an upward opening parabola that's been shifted down by 16. It's going to look something like that. I would probably label at least that intercept there as 0, -16. I might also label those. That's 4. And finally, the YZ trace is going to be very similar to the XZ trace. Because now for the YZ trace, what am I setting equal to 0? When I do that, I'm going to get Z equal to Y squared minus 16. And that's going to look exactly the same as this one over here. I'm just going to draw it now with my horizontal axis being Y, my vertical axis being Z, and getting the exact same shape. And that's how we draw all the traces. But the most important thing to remember when you're drawing a trace is whatever trace you're drawing, whatever variable is missing, that's the variable we're setting equal to 0. And that is the easiest way to do it. I suppose since we're asking it, we might as well ask the other question. Let's also find the intercepts. So what I would kind of think about here is the traces are kind of like two-dimensional intercepts. We are finding the 2D graph that's the intercept of the surface with the two-dimensional plane. Now we're just going to find the regular intercept. So if you're graphing a function y equals f of x, how would you find the y-intercept? Like if I was graphing y equals x squared plus 3x plus 2. I know the answer is going to be 2. But what am I doing to find the y-intercept? I'm setting, right, the other variable z equal to 0. So to find the x-intercept, it's really the same thing we just did here. The missing variables get to be 0. So to find the x, like I think, like now I say that, like, is that right, James? Yeah, that's totally right. You're going to set z equal to 0 and y equal to 0 and solve for x. So my x-intercept, well, if I have x squared equal to 16, I'm going to get x equal to plus or minus 4. So my x-intercepts are going to be 4, comma 0, comma 0, and negative 4, comma 0, comma 0. The y-intercept should be the same. And right, we can see that from the circle here, right? The x-intercepts are 4 and negative 4. The y-intercepts are negative 4 and 4. But for the y-intercepts, I'm going to set x and z equal to 0. I'm going to get 0 equal to 0 plus y squared minus 16. And I'm going to end up getting the same result. Y is going to be plus or minus 4. So my intercepts are 0, comma 4, comma 0, and 0, comma negative 4, comma 0. And finally, for my z-intercepts, I'm going to set x and y equal to 0. So I'm going to get z equal to 0 plus 0 minus 16. So z equals negative 16. So when you're finding intercepts or traces, set the missing variables equal to 0. For the x-intercept, I set y and z equal to 0. For the xy trace, I set z equal to 0. Whatever's missing gets to be 0. That will always work for intercepts and traces. Let's look at one more example of this because there is something I want to point out. Yeah, I don't want to do that. Yeah, sure. Let's do that. Paper. Sorry, I keep using my paper here. All right. So let's say I have two examples in mind. Let's look at this one first. Let's look at g of xy equal to, sure. I would imagine she could ask something like x plus y squared minus 4. To me, that seems like a fun one to do. Fun is probably an oversell there, James. It's not terrible. That's the best thing I can say about this one. So it's not terrible. And it's similar enough to your practice test questions, but just different enough that it's going to make you think. So let's find the intercepts first, because it's actually more normal to find the intercepts before you find the traces. And I don't think, no, she's not making you graph this. Cool. So let's find the intercepts. Okay. So let's start off with the x-intercept. We're going to set y equal to z equal to 0. We're going to get 0 equals x plus 0 minus 4. X equals 4. I don't think you need to write the 0.400, but you might need to. I think it's sufficient to say x equals 4, because you know that y and z are 0, but whatever. For the y-intercept, we're going to set x equal to z equal to 0. And we're going to get 0 equal to 0 plus y squared minus 4. We're going to get y squared equal to positive 4. We're going to get y equal to plus or minus 2. So our y-intercepts are 0, comma, plus or minus 2, comma 0. And thirdly, finding the z-intercept, so setting x equal to y equal to 0. We're going to get z equal to 0 plus 0 minus 4. So 0, comma 0, comma negative 4. Also, if you have the intercepts, it'll help you draw the traces. So now let's do the xy trace. So the xy trace, we're setting z equal to 0. And we're getting 0 equal to x plus y squared minus 4. Normally, I would say you should solve for y, because we're used to thinking of y as a function of x. But this is not one of those instances, because solving for y is kind of going to lead you down a path where you get y equals plus or minus the square root. And although it's not terrible, the better choice here is to actually isolate x and say that x is equal to 4 minus y squared. Let me ask you all a question. If I was graphing y equal to 4 minus x squared, which way would my parabola open? Up, down, left, or right? Down, right? Normal, right? Y equals 4 minus x or negative x squared plus 4, the parabola opens downwards. So now if I'm graphing x equal to 4 minus y squared, is my parabola going to open up, down, left, or right? It's going to be to the left. The reason why is if it's y equals 4 minus x squared, you're opening downward in the y direction or in the negative y direction. If it's x equals 4 minus y squared, you're opening in the negative x direction, which is to the left. You can also plot points, right? In fact, plotting points would be really helpful here. We have some intercepts. We know their x-intercept is 4, and our y-intercepts are plus or minus 2. The more I do this, the more I think it's a really good idea to find those intercepts before you find the trace. Because, oh yeah, looking at that, I'm even more convinced my parabola is opening to the left. And it is. Let's find the YZ. No, the XZ. It doesn't really matter what order you do this in. I'm just trying to be consistent. XZ trace. So Y equals 0. So setting Y equal to 0 here, I'm going to get, sorry, you can't quite see that. Z equal to X plus 0 minus 4, or just Z equal to X minus 4. X is the horizontal, Z is the vertical. And I know my x-intercept is still 4. And my z-intercept is negative 4. And I'm pretty sure it's a straight line because it's got the hallmarks of a straight line. So it's going to look like that. So I know I've said it twice already, but I'm going to say it again. It's really a good idea to find the intercepts first, because graphing your traces is much easier if you know what your intercepts are looking like. Finally, for your YZ trace, we're setting x equal to 0. And we're getting z equal to y squared minus 4, which is how I would leave it. And then I know that my z-intercept is negative 4. And my y-intercepts are plus or minus 2. And then we graph it. Cool. That was way easier when you had the intercepts, I think. Yeah. One more thing I want to say about trace, and then we can talk about something else. The other thing I wanted to mention about trace is that it's possible, although I don't really anticipate it, but it's possible someone could ask you to graph something where one of the traces was non-existent. Here's what I mean by that. Let's say we had something like, think for a second here. That 2 sheets. Yeah. Sorry, it's been a minute since I thought about this. That's kind of terrible. Yeah. You want, sure. Z squared minus x squared minus y squared equal to 4. Now, this might not be a great example because we're not writing z as a function of x and y. So let me change it just a little bit. Let's say z squared equals 4 plus x squared plus y squared. Is that going to turn out to be what I want it to be? Yeah, I think so. Okay. And then let's say z is equal to just the positive square root of 4 plus x squared plus y squared. So the function we actually want to look at is f of xy equal to the square root of 4 plus x squared plus y squared. I don't anticipate this coming up, but just in case, there's one thing I want to point out here. Intercepts are not a big deal, right? Z-intercept to x and y equal to 0, you're going to get z equal to the square root of 4 plus 0, which is just positive 2, not plus or minus. Y-intercept, you're going to set Z and X equal to 0. And so you're gonna get 0 equal to the square root of 4 plus 0 plus y squared. So you're gonna get 0 equal to the square root of 4 plus y squared, which you might notice is not gonna have a solution. If you square both sides, you get 0 equal to 4 plus y squared. You get y squared equal to -4. And while there are imaginary numbers that are solutions to that, we don't graph those, right? We don't graph it. We're not graphing imaginary numbers on this coordinate system, right? It's all real. So no solution. And the same thing for the x-intercept. Try to find the x-intercept. We're going to get 0 equal to the square root of 4 plus x squared plus 0, which is going to yield the same result. That's lovely. We've got one intercept, it's a z-intercept. Let's find the xy trace. Here's what I really wanted to get at. The xy trace, you're not going to have one. Because if you try to find the xy trace, well, if you set z equal to 0, then you're going to get 0 equal to the square root of 4 plus x squared plus y squared. But 4 plus x squared plus y squared is always bigger than or equal to 4. And so the square root of this is always bigger than or equal to 2, regardless of what values of x and y you pick. So this has no trace in the xy plane. On the other hand, it does have traces in the other two planes. In the xz plane, if you set y equal to 0, you're going to get z equal to the square root of 4 plus x squared. Which is kind of funky. It looks like this. If x is 0, z is going to be 2. And if x is, or negative, and then as x gets larger or negatively larger, z does this kind of deal. And then the same thing for the other one, the y, the z trace. You're going to get z equal to the square root of 4 plus y squared. Same kind of thing. I will point out, I'm not drawing a parabola there. It's not a parabola. I know it might look like a parabola. It's not a parabola. This line I've drawn, this curve I've drawn, actually has a slant asymptote. Parabolas do not have slant asymptotes. I know it's not important. Like if you drew this and you drew a parabola, you're fine. But like it's not a parabola. It's actually half of a hyperbola. And so the surface here, just so you all can know it, the surface I'm drawing here is half of a hyperboloid of two sheets. So it looks kind of like this. Kind of like a bowl. But it's not like the paraboloid, it's a hyperboloid. Yeah. Well, because look, here's the XY plane down here. Does my surface intersect that? No, it doesn't. But more easily seen to be none, because if you look at this equation, no matter what x and y are, x squared is bigger than or equal to 0. Y squared is bigger than or equal to 0. So x squared plus y squared plus 4 is bigger than or equal to 4. Which means the square root of that is going to be bigger than or equal to 2. And it can never equal 0. Since it can't ever equal 0, there isn't any x and y that solve this equation in the xy plane. That's why. It's kind of like taking, I'll have a good, okay. Here's my paraboloid, and it's sitting right here. And I'm asking you, what's the trace in the xy plane, which is the floor? Well, that doesn't touch the floor at all. So the trace or the intersection of this surface with the floor is non-existent. On the other hand, the other thing that I'm graphing, right, they would be surfaces that would drape over and go through the floor down to like the story below us. And then you would look at the intersection being like a circle or whatever, and that's the trace. So it's because our surface is entirely above or below the plane that we're interested in finding the trace in. Okay, cool. We have not a lot of time left, but there is at least one other thing I wanted to mention. Just to remind you all of these limit problems. I saw one in here that looked worthwhile. Yeah. So here's one that's not too terrible, I think. The limit as x, y approaches 0, 0 of x cubed plus y cubed over x to the fourth plus y to the fourth. And actually, this is an example of one where I don't think using the path x or y equals 0 is going to help. But let's look anyway. So if y equals 0, that is a path that goes to the origin. Then I'm going to rewrite my limit as the limit as x goes to 0 of x cubed plus 0 over x to the fourth plus 0. Simplifying that, you get the limit as x approaches 0 of 1 over x, which I guess doesn't exist. I mean, is that enough? I feel like it's not enough. It doesn't feel like the right way to do it to me. But maybe it is. But let's look at a different path. Let's look at, say, y equal to x. Limit as x goes to 0 of x cubed plus x cubed over x to the fourth plus x to the fourth, which is 2x cubed over 2x to the fourth. Oh, I forgot something. It's not that big a deal. I mean, it's kind of a big deal. I should have written the limit out here. And then that's still the limit as x goes to 0 of 1 over x, which still does not exist. I don't like this one that much. I mean, it's fine, but it's kind of not what we're used to seeing happen, where you pick like 2 different paths and you get 2 different actual values. I'm curious what her solutions say. This is 1-3. Sorry, there's only like a million of them to look at. Could you? Sorry. Always challenging here. Go away. Thank you. 2, 3 solutions. This is problem 2. Oh, no, that's totally valid. Okay. Sure. So if you're able to make it just not exist right off the bat, good on you. What about a different one? Because I feel like that's not very, it's not the question I would want to ask. I don't think it's that interesting. I don't feel like it's making the students really see the hard part about that question. So let's look at maybe a different practice test here and see if we can find one a little bit. Right, because 1 over 0, right? Literally, I mean, just like if you were asked in like a regular, 17A class, what's the limit as x goes to 0 of 1 over x? Oh, it doesn't exist. So it doesn't exist. We showed the limit didn't exist. That's all we were asked to do. This one is more, I think, my style. The limit is xy goes to 0, 0 of x squared y plus x over y cubed minus y. So here's what I wouldn't try. I wouldn't try y equal to 0. Because if I plug in y equal to 0, I'm automatically going to be dividing by 0, which is just not good. So let's go ahead and see if we can set x equal to 0. So do that, I'm going to the limit as y approaches 0, right? Whatever you're not setting equal to something, the other one still remains. And then I'm going to have 0 squared times y plus 0 over y cubed minus y. Let's simplify the top. What's 0 squared times y plus 0? Take the limit as y goes to 0 of 0 over y cubed minus y. Now here's the part we have to remember what happens. The denominator is not 0. It's getting close to 0, but it's not 0. What's 0 divided by 6? What's 0 divided by not 0? 0. What's 0 divided by 0? That's where the problem happens, but we're not doing that. We're saying we have 0 divided by something that isn't 0. And so before we take the limit, 0 divided by not 0 is just 0. Which is how it often plays out when you do the path along y equals 0 or x equals 0, is that the whole fraction becomes 0 before you take the limit. And the limit of a constant is just the constant value. Great. Now we just have to find some other path where the limit ends up being some other value. And looking at this, I would probably try y equals x. I don't know if it's going to work, but I'm going to try it. Why am I picking y equals x? Well, I see that if I pick y equals x, I'll have an x cubed on top and an x cubed on the bottom, and that seems good if the highest powers are the same. It might not work, but I'm going to try it, right? Sometimes you just have to try things. Where the limit is x goes to 0, x squared times x plus x over x cubed minus x. Okay, let's factor out. What can we factor out? On top, what can we factor out? And we're left with x squared plus 1. On the bottom, we can also factor out an x, and we're left with x squared minus 1. Cancel the x's we factored out, or divide them and get 1. And then the remaining thing, we can plug in 0, and we're going to get 0 squared plus 1 over 0 squared minus 1, which is 1 over negative 1, which is negative 1. And those are not the same. The limit does not exist. And it's definitely how I think we are meant to do this problem. Okay. Let's, in the last 6 minutes here, look at one of these Bayes formula questions. I think they're not terrible if you approach them in a certain way, I think. So I'm looking at this one from the final examination, I guess the actual final. Question 10 from the actual final. And so as I'm going to read this question, I'm going to write down what I think is pertinent as I read it. Suppose a certain disease has an incidence rate of 30%. So first of all, I'm going to say D is having the disease. And what we're saying with that sentence there is that the probability of having the disease is 30%. A test has been devised to detect the disease. The test does not, I hate these ones that don't produce false negatives, but whatever. The test does not produce false negatives. Okay. So let's say that A is testing positive, and then A complement would be testing negative. So I'm not writing down the things that I think are obvious, but it should be obvious to all of us that D complement is not having the disease, and A complement is testing negative. Okay, so the false positive rate is 5%. Okay, so a false positive is testing positive when you don't have the disease. So we're saying the probability of testing positive, given that you don't have the disease, is 5%. And they also told us that the test doesn't have any false negatives. So a false negative would be the probability of testing negative, given that you had the disease. What's the probability of that? 0. Okay. Based on these 3 pieces of information, I would then draw a tree. I cannot stress enough how useful I think it is to draw the tree. If you don't want to draw the tree, you can memorize the formula. That also works. It doesn't work for me. So here's the tree I'm talking about. On the first branch, it's always going to be, do you have the disease or not? You can have the disease with a 30% possibility, or you cannot have the disease with a 75%. Sorry, 75. Oh my God. You guys actually know the number with that probability that I'm not going to say. Okay, now the next branch up here is, given that you have the disease, what's the probability of testing positive or negative? Well, given that you have the disease, the probability of testing negative is 0%. Probability of testing positive is 100%, or 1. Given that you don't have the disease, what's the probability of testing positive? Oh, that's 0.05. What's probably testing negative? Well, it's got to be whatever's left over, which is 0.95. Cool. So now we're going to try and answer the question. suppose a randomly, I mean, I know what the questions are. Suppose a randomly selected person takes the test and tests positive. So so it is given that the person tested positive. What's the probability that they actually have the disease? Which is always the question we're asking with this kind of thing, right? Because that's what we care about. If you're right, you want to know, do I have this disease? So you're taking a test to see if you have it. And then you're worried about, well, if I test positive, what's the probability that I actually have the disease? So we're trying to find the probability of having a disease given that you had a positive test. Which should always be like the reverse conditional probability that you've actually been given in the setup. Note, again, I just want to point out here, notice I found some probabilities I didn't write down. We also found the probability of not having the disease given that you have a negative, the probability of testing negative given that you don't have the disease is 95%. And we found the probability of testing positive given that you have the disease is 100%. 1.00. So then I'm just going to look at my tree to figure it out. Oh, not quite. I'm going to do one other thing first. Let me remind myself that whenever it's a conditional probability, it's always the probability of the first thing and the second thing, or the intersection, divided by the probability of the given thing. And yes, there are more formulas you can write out here, but I would look at my tree and say, okay, well, if I want D and A, that's going to be first this, then this. So to get the probability of D and A, which sounds like I'm saying D and A, it's going to be 0.30 times 1 over all the ways you can get to having a positive test. Well, you can either have the disease and have a positive test, or notice that when I say the word or, I'm adding the next part, because that's how the words work with math. Or usually means add, and usually means multiply. I cannot have the disease and test positive. And that is our answer.